A simple command to a Mars rover takes over 20 minutes to arrive. This agonizing delay is the fundamental bottleneck of our current space age, a law of physics that limits everything we do beyond Earth. But a revolutionary technology is emerging that promises to shatter this barrier entirely. By the end of this, you will understand how we could soon control robots on distant moons in real time and build an unbreakable internet spanning the solar system. We will uncover how ghostly connections between particles could let us send information faster than light itself, and we will confront the monumental challenges of turning this science fiction dream into reality. What does a universe without waiting feel like to you? That 20-minute wait is more than an inconvenience. It is a wall. A mission controller sends a command to the Mars rover to drive forward. Then they wait. For over 40 minutes, they are completely blind to the rover's fate, unable to see if it has successfully navigated a rocky patch or if its wheels are suddenly slipping into a sand trap. This fundamental lag, dictated by the universe's ultimate speed limit, governs everything we do beyond our planet. It makes real-time control of robots on distant moons impossible. It turns a simple conversation with future astronauts on Mars into a stilted 40-minute exchange for every sentence. A critical equipment failure on a probe near Jupiter could occur, and we would not even know about it for over an hour, let alone be able to send a fix. This is not a problem we can solve with better antennas or more powerful computers. It is a law of physics, a barrier woven into the fabric of space and time itself. For our entire history of space exploration, this delay has been the silent, unyielding governor on our ambitions, defining the slow and cautious pace at which we can operate. But what if the universe itself offers a secret passage through this wall? Einstein's spooky action at a distance is not science fiction. It is a confirmed fact of our universe. Think of it not as two coins, but as a single, special pair of dice. When you roll them, they are completely normal and random, but the magic happens the moment you look at one. If you see it land on a 3, you know with absolute certainty that its partner, even if it is now on the other side of the galaxy, has also landed on a 3. This instant correlation is the heart of entanglement. It is a deep, fundamental link forged between two particles, a connection so profound that measuring one instantly sets the state of the other. This does not let us send a message screaming across space faster than light, at least not in the way you might think. You cannot force your die to land on a 6 to make the other one become a 6. The outcome of your roll is always random. The only thing that is not random is the perfect, instantaneous match between them. So if we cannot control the outcome, how could this possibly be useful for communication? The answer lies not in sending a message through the particles, but in using their spooky link to create a secret key that nobody else can ever intercept. This ability to hold multiple possibilities at once is the first, crucial step in writing our message to the stars. Think of a single photon not as a tiny bullet of light, but as a spinning coin caught mid-air. Before it lands, before anyone looks, it is not simply heads or tails. It is, in a very real sense, both. This is quantum superposition, the fundamental state of being for the smallest pieces of our universe. It is this strange, fluid reality that we must learn to harness. We take the simple, rigid language of our computers, the ones and zeros, and we translate them into this quantum dialect. We can encode a 1 or a 0 into the specific orientation or polarization of that spinning photon, but this is not an ordinary bit. This is a quantum bit, a qubit. A classical bit is a simple light switch, either definitively on or off. A qubit is that spinning coin, a probabilistic blend of both states, and this allows it to carry a depth of information a classical bit could never hold. This act of encoding is incredibly delicate. The moment you measure this qubit to read its message, the superposition collapses. The spinning coin lands, becoming a definite heads or tails. You get your answer, but the quantum magic is gone. So we have our message written in the most fragile ink imaginable, a language that destroys itself upon being read. How then do we send it across the cosmos without it fading away? The answer lies in the machine that forges the unbreakable link, the quantum source. That fragile quantum link, forged with such care, faces its greatest enemy on the journey to the stars, empty space itself. Over immense distances, a single photon carrying its precious quantum state is like a lone runner with a flickering torch, trying to cross a continent in a hurricane. The light can be absorbed by stray dust, its path bent by gravity, or its delicate quantum information simply scrambled by the noisy background hum of the universe. The connection breaks and the message is lost forever. To cross these cosmic gulfs, we cannot rely on a single, heroic particle. We must build a bridge. This is the purpose of the quantum repeater. Picture not a single runner, but a relay team stretching from Earth to Mars. Each member of this team holds one half of an entangled pair. The first runner on Earth is entangled with their partner at the first way station, 1,000,000 kilometers out. That station's other particle is entangled with the next station even farther away, and so on, creating a chain of linked particles. Now here is the real magic, a trick called entanglement swapping. The station at the first way station performs a special measurement on its two particles, the one linked to Earth and the one linked to the next station. This measurement does something extraordinary. It sews the two separate links together. The entanglement is transferred so that the particle on Earth and the particle at the second station become directly entangled, as if they had always been a pair. This process repeats hop by hop, station by station, extending the spooky connection like a cosmic zipper closing across the void. The final result is a single, continuous entangled link between a particle on Earth and a particle on Mars, a bridge built not of steel and cable, but of pure quantum correlation. It is this bridge that allows for quantum teleportation, the instantaneous transfer of a quantum state from one end of the bridge to the other. The message itself does not travel through space. It is dismantled here and reassembled there, using the entangled link as its blueprint. This chain of quantum repeaters is the indispensable infrastructure, the interstellar highway that transforms a lab experiment into a functional solar system internet. But with this bridge finally spanning the void, a pressing question remains: what kind of message do we send across it? This intricate dance of quantum teleportation is how information leaps across the cosmos without ever crossing the space in between. You have a sender, let us call her Alice, who holds the precious quantum state she wants to teleport, a single photon encoded with a message. She also holds one half of an entangled pair. The other half of that pair is with the receiver, Bob, who could be on Mars. Alice cannot simply look at her quantum state to copy it, because the act of looking, of measuring it, would destroy its delicate superposition. Instead, she performs a special joint measurement that entangles her message particle with her half of the entangled pair. This act is decisive. It instantly links the three particles together in a quantum embrace, but it also scrambles the original message state on her end. It is gone. At this exact moment, something remarkable happens on Mars. Bob's half of the entangled pair, which was previously in a random state, is now imprinted with the ghost of Alice's original message. But it is scrambled and unreadable, a locked chest without a key. Alice now sends Bob a simple, ordinary radio message. This message travels at the speed of light, taking 20 minutes to reach Mars. It contains not the message itself, but the instructions, the specific key needed to unlock the chest. When Bob receives this classical data, he uses it to perform a precise operation on his entangled particle. He turns the quantum key and the locked chest opens. The original quantum state, in all its complex superposition, is perfectly recreated on his particle. The information has not traveled, it has been reassembled, with the entangled pair providing the instantaneous connection and the classical message providing the final, crucial translation manual. This means the process is not faster than light, as we still have to wait for that classical signal, but it is fundamentally secure. The heart of the security lies in the laws of physics themselves. Any attempt to eavesdrop on the quantum channel, to intercept one of the entangled photons, would inevitably disturb their delicate state. Alice and Bob would instantly see the disturbance in their results, like noticing a fingerprint on a pristine surface. They would know the line was tapped and simply discard that compromised connection, generating a new one. This creates a communications channel where the very act of listening breaks the message, offering a level of security that is not just mathematically difficult to crack, but physically impossible to breach without leaving a trace. So we have the bridge and the secure transfer protocol. What then becomes possible when we weave this technology into the very fabric of our future in space? This inherent fragility of quantum information, the very thing that makes it so difficult to transmit, becomes its greatest strength when it comes to security. Imagine you are receiving a series of locked boxes, each containing a single piece of a secret code. With a normal box, a spy could open it, read the code, and then lock it back up again, and you would never know. But a quantum box is different. It is sealed with a mechanism so delicate that any attempt to open it, even for a split second, permanently changes its interior. The moment a spy peeks inside, they leave an indelible mark. When you receive the box, you can immediately see that it has been tampered with, and you simply throw that piece of the code away. This is the core principle of quantum key distribution, or QKD. It uses the quantum states of photons, their spinning coin orientations, to generate a random secret key. The sender, Alice, transmits a stream of these specially prepared photons to the receiver, Bob. After the transmission, they talk openly over a regular, unsecured channel. They compare notes on which measurement bases they used for a random subset of the photons. Where their choices matched, the results form their secret key. Where they did not, they discard the data. Now, here is the security check. If an eavesdropper, let us call her Eve, tried to listen in on the quantum channel, she would have to measure the photons to read the key. But because she does not know in advance how each photon was prepared, her measurements will randomly collapse the superpositions, introducing errors. When Alice and Bob publicly compare a small portion of their matching key bits, they will immediately see these discrepancies. The errors are the fingerprint of an intruder. The laws of physics have caught the spy in the act. They then discard the entire compromised key and start over, secure in the knowledge that their next attempt will be monitored by the unblinking eye of quantum mechanics. For a civilization stretching across the solar system, this is not a luxury. A command to alter the trajectory of a manned spacecraft, financial data from a corporate asteroid mining operation, or the private medical files of colonists on Mars, all of this requires a level of confidentiality that is absolute. Quantum key distribution offers a shield not based on complex math that might one day be broken, but on fundamental physical principles that are as immutable as the speed of light itself. But forging this unbreakable cipher in the tranquility of an Earth laboratory is one thing. Building it to survive the violent, unforgiving frontier of space is an entirely different challenge. The pristine silence of space is a lie. Between the planets, the void is a storm. It is filled with a relentless hail of cosmic rays, sleeting radiation from distant stars, and the constant, subtle pressure of sunlight itself. For a classical satellite, this is a manageable work environment. For a qubit, it is a war zone. That delicate superposition, the spinning coin state that holds our quantum information, is incredibly vulnerable. The slightest nudge from a stray high-energy particle, a random vibration, or even a tiny shift in temperature can cause it to collapse. This collapse is called decoherence, the death of the quantum state. It is the moment the spinning coin is slapped out of the air, forced to become a boring, ordinary heads or tails before we can even read it. Our entire quantum bridge depends on keeping these coins spinning, maintaining their coherence across millions of kilometers. On Earth, we achieve this with massive refrigeration systems, elaborate magnetic shields, and vibration dampeners that isolate the qubits in a near-perfect quietude. In space, we have to build a fortress around a ghost. The quantum memory devices that store our entangled pairs and the exquisitely sensitive photon detectors that read them must be shielded as if they were priceless ancient artifacts protected from a hurricane. Every component must be hardened against radiation and stabilized against the wild temperature swings between sunlight and shadow. But the challenge does not stop with protecting the qubits at rest. We also have to fire single photons, individual particles of light, across the solar system and have them hit a target the size of a dinner plate. This is not like aiming a laser pointer at a wall. This is like standing in New York and trying to thread a needle held by someone in London while both of you are on speeding trains. The slightest miscalculation in pointing, a tiny drift of 1/1000th of a degree, and the photon misses its detector entirely, lost forever in the infinite dark. The telescopes and optical systems that perform this feat must be engineered to an almost unimaginable precision, holding their aim steady against the subtle tremors of a spacecraft for years on end. This great engineering frontier, the battle to protect quantum coherence in the most hostile environment imaginable, is the price of admission for a quantum internet. So what is the prize that makes this Herculean effort worthwhile? The first practical applications will likely appear closer to home, not with a dramatic conversation with Mars, but in securing the orbital infrastructure that our modern world already depends upon. Imagine a network of quantum satellites in low Earth orbit, forming a secure backbone for global communications. A bank in Tokyo could execute a multi-billion-dollar transfer with a quantum key generated with a satellite, a key that is physically impossible to intercept. Government agencies could share intelligence with the absolute certainty that no third party was listening. This orbital quantum network would be the prototype, the testing ground where we work out the kinks of operating in space before we dare to stretch the chain to the moon. The next logical step is a quantum relay stationed at a Lagrange point, a gravitationally stable spot in space, acting as the first way station. From there, the chain extends. A quantum link to a lunar base could provide real-time, ultra-secure communication for astronauts, allowing them to control sensitive mining equipment or transmit scientific data without fear of interference. Each new node in this growing network brings us closer to the ultimate goal. The first interplanetary quantum link will not carry a dramatic message. It will likely transmit a single, secure key, a string of random numbers that will then be used to encrypt a conventional radio message. The process will be slow and methodical at first, a proof of concept. But in that moment when a secret created on Earth is instantly and securely present on Mars, the wall of delay will have gained its first permanent crack. The transformation begins not with a grand declaration, but with the subtle, instant twitch of a robotic arm. Picture a submarine probe descending into the dark, icy ocean of Jupiter's moon, Europa. On Earth, a pilot wearing a visor sees exactly what the probe's cameras see, a landscape of alien hydrothermal vents and strange, drifting life forms. She notices a fragile, crystalline structure ahead and instinctively nudges her control stick to the left. On Europa, millions of kilometers away, the probe responds without a single moment of hesitation. It glides smoothly around the obstacle, its movements a perfect mirror of human intention. This is the power of quantum communication applied to real-time control. The agonizing delay that forces our current robots to be slow, cautious, and largely autonomous simply vanishes. The quantum link provides the secure, instantaneous channel for command and feedback, while conventional radio, freed from the burden of secrecy, carries the high-definition video and sensor data. The human operator is no longer a distant commander sending orders into the void. They are sitting in the cockpit, their senses and reflexes extended directly into the alien environment. A robotic geologist on the jagged cliffs of a Martian canyon could be guided by a scientist on Earth to tap a specific, promising rock layer, feeling the resistance through haptic feedback as if they were holding the hammer themselves. This immediate connection turns every mission from a pre-programmed sequence of cautious moves into a dynamic, interactive exploration. The robot becomes a true avatar, its actions infused with human curiosity and expertise in the very moment of discovery. The implications for science are staggering. Instead of spending days planning a single 10-meter drive for a Mars rover, a team could cover kilometers in an afternoon, reacting to new finds as they happen. A probe flying through the geyser plumes of Saturn's moon, Enceladus, could identify complex organic molecules with its onboard lab, and immediately, upon that discovery, be commanded to alter its course to sample an even richer part of the plume, all within seconds. This real-time partnership between human and machine dramatically accelerates the pace of discovery and radically improves mission safety. Hazards that would mean certain doom for an autonomous robot, like a sudden dust devil on Mars or a collapsing ice bridge on Europa, can be seen and avoided with human reflexes. The quantum bridge does not just send data faster, it closes the loop of perception and action, weaving human intelligence directly into the fabric of exploration across the solar system. And this is only the first application for the robots that go where we cannot. What happens when we build a network that connects human colonies directly to this web of instant communication? That seamless, instantaneous control of distant robots is just one thread in a much larger tapestry. The true power of this quantum bridge emerges when we weave it into the very infrastructure of a spacefaring civilization. Right now, what we call the interplanetary internet is a fragile, slow-motion patchwork. It relies on a store and forward system where data packets are painstakingly transmitted across the void, received by a deep space antenna, stored on a server, and then slowly forwarded to the next hop. A high-definition image from a Martian rover can take hours to fully arrive on Earth. This is the digital equivalent of sending letters by sailing ship. A quantum backbone would replace this with a continuous high-capacity superhighway. It would link every asset, from satellites in orbit around different worlds to habitats on the surface and spacecraft in transit, into a single, cohesive web. This network's nervous system would be built from chains of quantum repeaters, creating dedicated, secure channels for the most critical data. but its arteries would carry the lifeblood of civilization, immense rivers of raw information flowing without delay. Consider a radio telescope nestled in the perpetual darkness on the far side of the moon, shielded from Earth's electronic noise. Today, getting its data back to scientists would be a bottleneck of compressed transmissions and long waits. On a quantum internet, that same telescope could stream a fire hose of pristine, uncompressed data in real time, delivering a live, ultra-high-definition window into the deepest cosmos. This is not just about faster downloads, it enables a new mode of collaborative science. A researcher in Berlin could manipulate the telescope's settings, while a colleague in Tokyo analyzes the incoming data stream, both interacting with the instrument as if it were in the room next door. For human colonies, the impact is even more profound. A family on Mars would not have to wait 20 minutes to see the reaction to a joke told to relatives on Earth. They could share a live, lag-free video call, watching their grandchildren take their first steps in real time. This erases the profound isolation of space, shrinking the psychological distance between worlds and fostering a sense of a single, connected society scattered across the solar system. This quantum backbone becomes the indispensable utility for a multi-planetary species, as fundamental as power and water. Yet its ultimate promise may be even stranger, reaching beyond communication to probe the deepest mysteries of the universe itself. The ultimate promise of this quantum bridge extends far beyond communication and control, reaching into the very heart of reality. We have built our understanding of the universe on two monumental pillars: the theory of the very large, Einstein's general relativity, which describes gravity and the curvature of spacetime, and the theory of the very small, quantum mechanics, which governs the bizarre world of particles. The problem is, these two theories refuse to talk to each other. They are written in different languages, and where they should meet, at the edge of a black hole or the first moment of the Big Bang, our physics breaks down into paradox. To find a theory of everything, we need a laboratory of unparalleled scale, one that can test the foundations of physics in ways no Earth-bound experiment ever could. The solar system itself becomes that lab. Picture a single entangled pair of particles, but with one half held in a lab on Earth and its partner placed in a satellite orbiting Jupiter. By performing precise measurements on these particles across billions of kilometers, we can ask profound questions. Does the immense gravitational field of Jupiter, warping the fabric of spacetime around it, have any effect on the spooky link between the particles? Does entanglement, this ghostly connection, feel the pull of gravity? We simply do not know. Such an experiment would probe the frontier where quantum mechanics and general relativity intersect, a no-man's land where new physics is almost certainly hiding. We could test whether the fundamental constants of nature are truly constant everywhere, or if they subtly change in different gravitational environments. Each quantum repeater station, from Mercury to the outer planets, becomes not just a communications node, but a fundamental physics outpost, collecting data that could finally help us sew the fabric of physics back together into a single, coherent picture. Making this cosmic laboratory a reality falls to a new generation of pioneers, the scientists and engineers who are already building the first pieces of this quantum future. The race to build this quantum future is already underway, a global competition unfolding not with grand announcements, but in the quiet hum of laboratories and the precise trajectories of satellites. Leading space agencies and private companies are all pushing to demonstrate that these delicate quantum technologies can not only survive the violent ride to orbit, but also function flawlessly in the harsh environment of space. China's Misha satellite stands as a landmark achievement in this quiet race. It has successfully generated entangled photon pairs in orbit, and beamed them down to separate ground stations over 1,000 kilometers apart, performing quantum key distribution between the Earth and space. This was not a simulation. It was a working prototype in the vacuum, proving that the core principle of a quantum link could be extended beyond the atmosphere. Now, the focus is intensifying on the next generation of hardware. Engineers are striving to shrink the bulky, refrigerator-sized quantum optics labs of today into rugged, miniaturized packages no larger than a shoebox. These space-hardened quantum sources and ultra-sensitive single-photon detectors must be designed to withstand the bone-shaking vibrations of a rocket launch and the extreme temperature swings they will encounter in orbit. The International Space Station is becoming a vital testbed for these technologies, with plans to install quantum communication terminals that can establish secure links with ground stations. Every successful test, every data point collected from these orbital prototypes, is a brick being laid in the foundation of our interplanetary internet. The next major milestones are clearly taking shape. We can expect to see the first demonstrations of quantum key distribution between two moving satellites, a critical step for building a resilient space-based network. Following that, the goal will be to establish a continuous quantum link between the Earth and the Moon, pushing the distance envelope by an order of magnitude. Each of these achievements solves another piece of the puzzle, from mastering long-distance pointing and tracking to proving that quantum memories can maintain their coherence for the required time in microgravity. This methodical, step-by-step progress transforms the seemingly magical concept of instantaneous cosmic communication into a series of solvable engineering problems. With each prototype that survives its mission, the dream of a quantum-connected solar system moves from the realm of theoretical physics into the concrete plans for humanity's future. This stepwise expansion into the cosmos begins right where we are today, in the relative backyard of low Earth orbit. Satellites whizzing a few hundred kilometers overhead are our training wheels, allowing us to perfect the delicate dance of sending and receiving quantum states with a moving target. Every successful key exchange between a ground telescope and a passing satellite is a vital data point, proving the technology can function outside the pristine isolation of a lab. But the real test of our quantum metal is the Moon. Bridging the 400,000-kilometer gulf to our celestial neighbor is a staggering leap in difficulty. The precision required is akin to hitting a coin in Paris with a laser pointer held in New York. Only both the coin and the pointer are in constant, predictable motion. Over that distance, even the faintest whisper of a quantum signal is stretched to its absolute limit, demanding detectors of almost supernatural sensitivity and optical systems of flawless stability. A stable lunar quantum link would be our first true demonstration that this technology is ready for interplanetary distances. It would provide a secure, instantaneous channel for a future lunar base, transforming it from an isolated outpost into a fully integrated node in a growing network. But the ultimate prize, the goal that redefines our relationship with the solar system, is Mars. An Earth-Mars quantum channel cannot be a single, heroic laser beam. The distance between the two planets is not static. It fluctuates wildly from a relatively close 60 million kilometers to over 400 million kilometers when they are on opposite sides of the Sun. At its greatest expanse, the signal loss would be catastrophic for a direct link. The only viable solution is to construct a celestial chain, a series of quantum repeater stations positioned at strategic points in space. One repeater might be placed in an orbit closer to the Sun than Earth, while another is stationed farther out, creating a relay path that can always find a way around the solar obstruction. This network would be the most ambitious infrastructure project humanity has ever undertaken, a backbone of pure information stretching across the inner solar system. Each step in this roadmap, from low orbit to the Moon and finally to Mars, builds not just the technology, but the confidence to take the next leap. Yet, for all the progress, the path forward is paved with monumental challenges that will test the limits of our engineering and our patience. The whisper of a quantum state is the most fragile thing we have ever tried to send across the cosmos. That delicate superposition, the particle's ability to be in multiple states at once, must survive a journey of months through a vacuum that is far from empty. It must endure the relentless sleet of cosmic radiation, the subtle tug of magnetic fields, and the faint but constant pressure of starlight. Any one of these encounters, even a single stray photon from a distant star, can nudge the particle. And in that moment, the quantum magic vanishes. The spinning coin is slapped down, forced into a definite state. This is decoherence, the silent killer of quantum information, and over interplanetary distances, it is the rule, not the exception. To cross this gulf, we need more than a perfect signal, we need a perfect memory. The quantum repeater stations that form the links in our cosmic chain cannot simply receive and retransmit a photon. They must capture the photon's quantum state and store it within a quantum memory device, holding that fragile whisper intact for hours, days, or even longer, until the next link in the chain is ready. This demands materials of almost impossible purity. Imagine a crystal so perfect that not a single atom is out of place, a structure so quiet that a quantum state can reside within it, undisturbed, for an unprecedented length of time. Scientists are exploring everything from specially engineered diamonds with atomic-scale defects to clouds of ultra-cold atoms held in magnetic traps, all in search of that perfect quantum vault. But even the best vault can develop a crack. This is where quantum error correction comes in, a concept that bends the mind. In a classical computer, you can simply copy a bit over and over for backup. But you cannot copy a qubit. The no-cloning theorem of quantum mechanics forbids it. Any attempt to measure the qubit to check its status would collapse it. So how do you correct an error without looking? The solution is as brilliant as it is strange. Instead of storing the information in a single particle, you spread it out across several, weaving them together into a logical qubit. You then carefully measure the relationships between these particles, not their individual states. This is like listening to a chorus without distinguishing any single voice. From the harmony of the group, you can detect a single sour note, a single particle that has decohered, and you can mathematically correct it without ever knowing what the original message was. You fix the whisper by listening to the echo it creates in the ensemble, building a system that can perform this delicate ballet autonomously, millions of kilometers from any human repair, is one of the most daunting physics and engineering challenges we have ever faced. It is the absolute prerequisite for a chain of trust that can stretch from one world to another. The faint whisper of a single photon must find its way home across millions of kilometers of emptiness. This is not a floodlight, but a precisely aimed laser beam so narrow that by the time it reaches Earth, its footprint could span an entire continent. Hitting a detector the size of a coin with that beam is the engineering equivalent of a golfer on Mars sinking a hole in one on a green in Paris. The slightest tremor in the spacecraft, a tiny miscalibration in its orientation, or a subtle drift in its alignment would send the photon veering off into the eternal dark, its precious quantum message lost forever. The laser systems responsible for this must be monuments to stability, isolated from the vibrations of the spacecraft's own systems and locked onto their target with a precision measured in fractions of a microradian, a unit of angle so fine it would take thousands of them to equal the width of a full moon in our sky. But even a perfectly aimed signal faces a final, turbulent barrier, our own atmosphere. The air around our planet is a seething, chaotic lens, heat rising from the ground, pockets of different air density, and the constant churn of weather all bend and distort light, smearing a perfect laser beam into a useless, blurry patch. To counter this, ground-based telescopes employ adaptive optics, a remarkable technology that fights fire with fire. It uses a bright guide star, either a real star or a laser beam projected into the upper atmosphere, to measure the distortion in real time. A computer then commands a deformable mirror, a surface with hundreds of tiny actuators, to change its shape thousands of times per second, actively cancelling out the atmospheric blur and sharpening the quantum signal back into a pinpoint. And at the end of this impossible journey, the photon must be seen. Ordinary light sensors are too noisy and insensitive to reliably detect a single particle of light that has been weakened by its epic voyage. The answer lies in superconducting nanowire single photon detectors. These are exquisitely delicate circuits, chilled to temperatures colder than deep space, where electricity flows without resistance. When that lone, weary photon finally arrives, it strikes a wire so fine it is barely there, causing a tiny, localized hotspot. This minute change in temperature is enough to break the superconductivity for an instant, creating a measurable electrical pulse. It is the most sensitive doorbell in the universe, ringing just once for the most important guest imaginable. Beyond these monumental technical barriers, the future of this technology will be shaped by forces far removed from the laboratory, by the complex interplay of global ambition, economic investment, and international cooperation. The race to master quantum communication is more than a scientific endeavor. It is a high-stakes contest for the ultimate strategic high ground. The nation or corporation that first deploys a functioning interplanetary quantum network will command the solar system's most valuable asset, absolute information supremacy. This is not just about faster downloads, it is about controlling the nervous system of a spacefaring civilization. Military commands could be issued with unbreachable security. Financial transactions for asteroid mining could be executed with perfect confidentiality, and scientific data from the farthest probes would flow through a single, proprietary channel. This creates a new form of power, a quantum sovereignty where control over the communication lanes equates to control over the activities they enable. The ability to guarantee secure, instantaneous dialogue between Earth and a lunar factory or a Martian colony would be the foundation of economic and political influence for the next century. Such a monumental advantage will not go uncontested. We could be witnessing the dawn of a new kind of space race, one not focused on planting flags, but on deploying quantum repeaters and locking down the spectral real estate of laser communications. The fear of being left behind, of becoming digitally isolated in a connected solar system, will drive nations to invest billions and accelerate their programs, potentially creating a tense and fragmented environment where every new quantum satellite is viewed as a strategic asset. This powerful technology, born from the quest for knowledge, could inadvertently divide us unless we consciously choose a different path. The alternative to a fractured quantum future is a framework of international cooperation, similar to the treaties that govern Antarctica or the principles for the peaceful use of outer space. Global standards for quantum frequencies, protocols for interoperable networks, and agreements on the neutral use of quantum repeaters at Lagrange points would be essential. We have a profound choice to make. Will this quantum bridge become a private toll road for a single power, or an open highway for all of humanity? The rules for this new frontier are being written right now in laboratories and government offices around the world. This leads us to the final and perhaps most profound question of all: what becomes of humanity when we are truly, instantly connected across such vast, silent distances. The final frontier for this quantum bridge is not Mars, but the void between the stars. A probe like Breakthrough Starshot, a tiny craft propelled by light sails on a 20-year journey to Alpha Centauri, would face a communication nightmare. Using conventional radio, its first close-up image of an alien world would take over 4 years to reach us, a slow trickle of data from a long, silent messenger. But if that nanocraft carried a miniature quantum source, the story changes entirely. It could depart our solar system with one half of an entangled pair, while we keep the other half secure in a station orbiting Pluto. As the probe travels, this spooky connection would stretch across the light years. The moment its cameras capture that first, blurry image of a new Earth, it could use quantum teleportation to send the image data home. The information would be reassembled here instantly. We would not see the image 4 years after it was taken. We would see it the very instant the probe does. This transforms a one-way data dump into a live scientific feed. A critical sensor reading indicating potential biosignatures could be analyzed by scientists on Earth within hours, not decades, allowing them to send new instructions back to the probe, guiding it to investigate further. The data rate would be incredibly slow, a thin trickle of the most precious bits, but it would be a real-time thread tying us to our first interstellar ambassador. This staggering possibility forces us to confront a deep philosophical puzzle. That entangled pair connecting Earth to a probe light years away defies our everyday understanding of location and connection. Where does the information truly exist? Is it on the probe, or is it here with us, simply waiting to be unlocked? Quantum mechanics suggests that until a measurement is made, the reality of that data is spread across the entire link, a ghostly presence spanning light years. This challenges the very idea of here and there. We are forced to consider that the universe at its most fundamental level might not be a collection of separate points in space, but a single, deeply interconnected whole. Building a quantum bridge across the solar system is the first practical step toward discovering if the stars themselves are already linked by a web we are only just beginning to perceive. This instantaneous link across the cosmos directly confronts one of our most basic assumptions about reality, that cause must always precede effect. We are wired to believe that for one thing to influence another, a signal must travel between them, a process that takes time. Yet with entanglement, measuring a particle here instantly sets the state of its partner, even across a gap of light years. No signal travels, no time elapses. The effect is simply correlated. This is not a breakdown of physics, but a profound revelation that our classical billiard ball understanding of cause and effect is incomplete. It forces us to accept that the universe possesses a deeper layer of connection, one that operates outside the familiar confines of space and time. This challenges the principle of locality, the comforting idea that an object is only directly influenced by its immediate surroundings. Entanglement suggests that at a fundamental level, the entire universe might be woven together with threads of instantaneous correlation, a seamless whole rather than a collection of separate, isolated points. Successfully building a quantum bridge to Mars would do more than just send data. It would be a monumental, practical demonstration that this interconnected reality is not just a theoretical curiosity. It is a tangible feature of our cosmos, one we can literally plug into. This forces a paradigm shift in our cosmic worldview, from seeing space as a vast emptiness separating islands of matter to understanding it as a medium for a deeper, more immediate unity. The very concepts of here and there begin to lose their absolute meaning when 2 points can share a single quantum state. Such a profound rewriting of our cosmic perspective, however, arrives with its own set of formidable risks. The power to communicate with absolute security and without delay is a tool of immense strategic value, and like any powerful tool, its application rests entirely in the hands of its users. The very property that makes quantum communication unbreakable, its sensitivity to eavesdropping, could be turned into a weapon. An adversary would not need to crack the code. They could simply attempt to disrupt the quantum channel itself. A well-aimed laser dazzling the sensitive detector on a quantum satellite could blind it, severing the secure link at a critical moment. This is not traditional jamming. It is quantum denial of service, an attack on the physical layer of reality that the system depends on. Furthermore, the concentration of such perfect communication capability could create a new kind of dependency and vulnerability. If all critical command and control for a Martian colony flows through a single quantum channel, the failure of one key repeater station, whether by space debris, sabotage, or simple engineering flaw, could isolate that colony entirely, cutting the instantaneous lifeline and forcing a fallback to the agonizing delays of conventional radio. The stakes of a system failure become astronomical. This technology, born from the quest to overcome a fundamental limit of the universe, forces us to confront a very human limit, our capacity for responsibility. We must build not only the quantum repeaters to bridge space, but the diplomatic and security frameworks to ensure this awesome power fosters connection and discovery, rather than conflict and control. That same unbreakable channel, a marvel of physics, could become the perfect instrument for conspiracy. The absolute security that protects a colony's medical data also provides a flawless veil for those with malicious intent. A hostile group could use a private quantum link to coordinate an attack on a rival outpost or to hijack an automated cargo freighter, all while their communications remain entirely invisible to any form of interception. There would be no wire to tap, no signal to jam, only the silent, certain knowledge that a plot is unfolding in a bubble of perfect secrecy. This is the paradox of perfect security. It protects the innocent and the guilty with equal, indifferent efficiency. The network's fragility introduces another layer of risk. Our growing dependence on this instantaneous link creates a single point of catastrophic failure. A massive solar flare, a cloud of micrometeoroids, or a deliberate act of sabotage against a key quantum repeater station could shatter the chain in an instant. The consequences would be immediate and severe. On Mars, a mining operation relying on real-time control from Earth would suddenly find its robotic avatars frozen, their human operators staring at blank screens 20 light-minutes away. A deep space probe navigating a treacherous asteroid field would be struck blind and paralyzed, left to the mercy of its last uploaded command. The very system designed to eliminate delay could, in a moment of failure, create a silence more profound and dangerous than the lag it replaced. Building this quantum future therefore demands more than just technological genius. It requires a parallel development of social and political architecture. We will need robust, automated fail-safe systems that can instantly switch critical functions to autonomous modes or reroute through slower, but more resilient classical channels. More importantly, we must forge international treaties and usage protocols long before the first interplanetary quantum node goes online. These agreements would need to establish clear rules for neutral access to repeater stations, define acts of quantum aggression, and create frameworks for cooperation in the event of a network-wide emergency. The question is no longer just if we can build this bridge, but what kind of traffic we will allow to cross it. Will we use this godlike power to weave the solar system together in a web of trust and shared discovery? Or will we balkanize space into armed camps connected by unbreakable secret lines? The next few decades of research and diplomacy will determine whether this quantum bridge becomes our greatest achievement in cooperation or our most sophisticated tool for conflict. The next 10 years will transform our planet into a planet wired with light. Global quantum internet backbones will begin linking major financial hubs, government centers, and research institutions, not as isolated experiments, but as critical public utilities. Imagine the data flows of a city like London or Singapore being encrypted with keys generated by the fundamental laws of physics, making financial markets and power grids inherently resilient to digital eavesdropping. This terrestrial network will be the stable, proven foundation upon which we will build our cosmic expansion. Simultaneously, our focus will pivot upward to the stark, gray landscape of the Moon. The goal for the 2030s is unambiguous: to establish a reliable, continuous quantum link between Earth and a permanent lunar base. This will not be a single, heroic experiment like the first laser beam reflected off a retroreflector. It will be an operational system. We can expect to see quantum-capable payloads integrated into the next generation of lunar orbiters, acting as dedicated communication nodes. These satellites will do more than just test the technology. They will provide the secure, instantaneous command channel for the astronauts and robots operating below. Every soil sample analyzed, every habitat system monitored, and every high-definition video stream from the lunar surface could be secured by a quantum key, making the base's digital nervous system immune to interference. The true engineering marvels of this period, however, will be the first prototype quantum repeaters designed for cislunar space. These will not be the massive multi-planet stations of the future, but smaller, ruggedized units tested in the relative proximity of the Earth-Moon system. Their mission will be to prove that entanglement swapping and quantum memory can function autonomously in the high-radiation environment beyond low Earth orbit. Each successful test of a repeater link between a satellite near the Moon and a ground station on Earth is a rehearsal for the much grander performance to come at Mars. This decade is the crucial bridge. It is when we stop marveling at the quantum magic in our laboratories and start relying on it to run an outpost on another world. The 2030s will be remembered as the decade we truly became a quantum-connected species, first on our home planet and then, decisively, at our nearest celestial neighbor. Managing a web of quantum repeaters stretching from Earth to Mars will be a task of impossible complexity for any human team. The network will not be a static highway but a living, breathing entity, with connections constantly forming and breaking as planets move, repeaters drift, and the environment shifts. This demands a conductor with superhuman speed and perception, an artificial intelligence serving as the network's brain. These AI systems will operate in real time, making millions of microscopic decisions every second. Their first and most critical job is resource allocation. Entanglement is a finite resource, a fragile commodity that must be generated, stored, and distributed with exquisite timing. The AI will act as a cosmic air traffic controller for quantum states, deciding which entangled pairs to use for a high-priority military command, which to hold in reserve for a scientific data stream, and which to sacrifice for routine network diagnostics. It will dynamically route information, finding the optimal path through the web of repeaters to avoid a solar storm disrupting one link or a failed memory unit in another. But the AI's role goes far beyond simple routing. It will be the network's physician, constantly diagnosing its own health. By analyzing the success rates of quantum teleportation across different channels, the AI can detect the faintest signs of decoherence in a distant repeater's memory unit. It can diagnose a misaligned telescope on a satellite orbiting Jupiter by noticing a specific pattern of signal loss, and most importantly, it can prescribe the cure. The AI will command the network's built-in quantum error correction systems to spring into action, stabilizing wobbly qubits and repairing corrupted logical qubits before the information is lost. It will continuously fine-tune the laser power, adjust the pointing systems, and recalibrate the detectors, squeezing every last bit of performance from the hardware. This is not a system we will command, it is a system we will trust. The synergy between the deterministic world of artificial intelligence and the probabilistic, spooky world of quantum physics is what makes the entire enterprise feasible. Without an intelligent, autonomous nervous system to manage the quantum magic, the dream of an interplanetary internet would collapse under its own complexity. The staggering cost of a solar system internet will be its ultimate gatekeeper. We are talking about infrastructure investments that could reach into the trillions of dollars, a scale that dwarfs any single national budget. Government space agencies will undoubtedly lay the foundation, funding the initial research, launching the first experimental satellites, and proving the core technology works. They are the only entities with the patience and deep pockets for such high-risk, long-term science. But for this network to grow from a few fragile proof of concept links into a robust, resilient utility spanning the planets, it will need a more powerful and sustainable engine, the engine of commerce. The very businesses that will define the next era of space exploration will become the network's most demanding customers. An asteroid mining operation needs to transmit its mineral assay data back to Earth with absolute confidentiality, as that data is the core of its stock value. A factory in lunar orbit manufacturing delicate fiber optics in microgravity requires real-time telemetry and control from engineers on Earth to manage its complex processes. A luxury hotel viewing the rings of Saturn needs to offer its wealthy guests lag-free, high-definition video calls with their families back home. For these ventures, a quantum communication link is not an exotic luxury, it is a critical business requirement. This commercial demand will birth an entirely new industry, a private sector dedicated to building, launching, and operating the quantum repeaters and satellites that form the network's backbone. This transforms the quantum bridge from a magnificent scientific achievement into a profitable utility, a piece of critical infrastructure as essential as a power grid. The revenue generated from selling bandwidth and security to these space-based enterprises could then be reinvested to extend the network further, to the moons of Jupiter and beyond, creating a virtuous cycle of economic growth and technological expansion. The business case for a quantum cosmos is not yet fully written, but the first chapters are being drafted in corporate boardrooms that see the final frontier not just as a place of discovery, but as the next great marketplace. For generations, the dream of speaking to someone on another world without a moment's pause has lived only in the pages of science fiction. To actually hold such a conversation would fundamentally reshape our perception of the solar system. Mars would no longer feel like a distant, isolated frontier. It would become a place you could call a neighborhood in the cosmic city. This tangible connection makes the vision of a multi-planetary society feel less like a far-off aspiration and more like an imminent reality, knitting separate worlds into a single, cohesive community. The cultural ripple effects would be immense, likely inspiring a new wave of scientists and engineers. Just as the grainy images of astronauts walking on the moon ignited the ambitions of an entire generation, the first live, lag-free video call from a Martian colony could define the dreams of the next. It presents the cosmos not as an impassable void, but as a place we are actively and intimately joining together. Yet this profound shift also casts a long shadow. The very technology that connects worlds could create a deep chasm right here at home. A new, stark digital divide would emerge, not between the connected and the unconnected, but between those on the instant quantum network and those stuck on the delayed classical channels. A research team with quantum access could receive and analyze data from a Jovian moon in real time, while a university relying on public data streams would wait for hours or days for the same information. A corporation using quantum links could execute interstellar trades and control automated factories with perfect security, while smaller competitors are left in the slow lane, operating at a permanent disadvantage. This is not merely an issue of bandwidth, it is a question of access to a new dimension of time and security. The societal implications are vast. Will quantum communication become a public utility, managed for the benefit of all humanity, or will it be a privatized luxury, amplifying existing inequalities on an interplanetary scale? Managing these expectations and ensuring this powerful tool fosters inclusion rather than division is a challenge as monumental as building the quantum repeaters themselves. Ownership of the very data flowing through these quantum channels is the first great ethical frontier. If a scientist on Earth uses a quantum link to control a robot that discovers a new microbe on Europa, who owns that discovery? Is it the scientist, their government, the corporation that built the repeater station, or all of humanity? This question extends to the most personal information. A colonist on Mars undergoing medical treatment transmits their quantum-encrypted genomic data to a specialist on Earth. That data is secure, but where does it reside, and who has the right to access or use it after the diagnosis is complete? The instantaneous nature of the link creates a sense of intimacy, but it also risks turning personal lives into data streams managed by distant entities. We must define what privacy means when your most sensitive communications are logged by a network spanning planets. Does the right to be forgotten extend to data stored on a lunar server? These are not abstract questions. They are the foundation of individual autonomy in a connected solar system. The power to influence events across millions of kilometers in real time carries its own profound moral weight. A corporation on Earth could use its priority quantum access to instantly shut down a rival's mining operation on an asteroid, citing a safety violation without any possibility of immediate local oversight. A government could leverage its control over a key repeater node to exert political pressure on a developing Martian settlement, creating a new form of light-speed imperialism. This technology could enable a central authority to micromanage distant colonies with an efficiency that stifles local independence and innovation. The very tool designed to unite us could become the ultimate instrument of remote control. To prevent this, we cannot rely on the goodwill of any single nation or corporation. The scale demands a new social contract, a framework of cosmic ethics developed through a multi-planetary governing body. This body would not seek to control the technology itself, but to establish the rules for its use, creating a universal bill of digital rights for the space age. It would arbitrate data ownership disputes, enforce privacy standards across worlds, and protect smaller colonies from coercion by ensuring neutral access to the quantum backbone. Building this network is a test of our technological maturity, but establishing its ethical foundation is the true measure of our wisdom as a species. The quantum bridge grants us a power that mirrors that of the gods, and with it comes the solemn responsibility to ensure it builds a fairer, more united civilization, not a tapestry of new conflicts written across the stars. The ultimate destination for this technology is a web of light spanning the galaxy itself. If humanity one day builds arcs to travel between stars, we will not leave our quantum connections behind. A future network could consist of nodes positioned in the cold, stable darkness between stars, at gravitational anchor points like the Oort clouds of neighboring suns. These stations would form a galactic internet, a backbone of instantaneous, secure communication binding together a truly interstellar civilization. A discovery made by scientists orbiting a star in the Orion Arm could be shared with researchers on Earth in the very moment of its realization, collapsing the light years of separation into a single, shared point of understanding. This vision forces us to confront the most profound question of all. If we are on this path, then other intelligent species, likely far older and more advanced, must have already mastered these principles. For decades, our search for extraterrestrial intelligence, SETI, has scanned the skies for the faint whispers of radio waves, a technology we ourselves are rapidly outgrowing. It is like searching for smoke signals in a world that has invented the telephone. A civilization spanning multiple star systems would not rely on the slow, leaky broadcast of radio. It would use a quantum network, a system that is inherently targeted, secure, and efficient. This completely reframes the search. Future SETI programs might not listen for a message, but instead look for the ghostly fingerprint of the communication channel itself. Our telescopes would be tuned to detect the distinct, unnatural signatures of quantum entanglement distribution, perhaps a very specific pattern of photons that could only be produced by an artificial source. We would be searching not for a signal in the noise, but for the silent, perfect correlation that betrays a technology operating on a galactic scale. Mastering quantum communication, therefore, is more than a project for our own convenience. It is the first, crucial step in learning to speak the universe's native language, a language built not on sound, but on the instantaneous links that underpin reality itself. Our journey from a 20-minute delay to Mars ends here, at the threshold of a cosmos where distance is no barrier to connection, and where our first conversation with another intelligence may not be an exchange of words, but a simple, mutual recognition of the same spooky thread woven through the fabric of space and time. We began with a simple, agonizing wait, a 20-minute command to a rover on Mars. That delay, dictated by the universe's ultimate speed limit, has defined our entire history of space exploration. From that starting point, we have ventured into the strange and wondrous world of quantum physics, unraveling the secrets of spooky action at a distance and the magic of quantum teleportation. We have seen how fragile entangled particles could form an unbreakable bridge across the solar system, built link by link with quantum repeaters stationed in the void. The challenges are monumental, from protecting these delicate quantum states against the harshness of space to aiming single photons with God-like precision. Yet the potential rewards are equally staggering. Imagine controlling a robot on a distant moon as if your own hands were there, or building an internet for the solar system secured by the immutable laws of physics. This journey has taken us from a fundamental limitation to a vision of profound connection, where the very act of communicating across millions of kilometers could help us test the deepest laws of reality. The engineering hurdles are immense, but the relentless pace of innovation in laboratories and in orbit tells a clear story. The end of the space delay is not a question of if, but of when. This is not just a new technology, it is a new chapter for humanity. It promises to weave our scattered outposts into a single, cohesive society, to protect our interplanetary conversations with perfect security, and to offer us a front-row seat to the universe's greatest mysteries. The quantum future is no longer a dream sketched in science fiction. It is a blueprint being drafted in clean rooms and coded into simulations today. It is a future without waiting. We would love to hear which possibility excites you the most. Is it the real-time control of robotic avatars on distant worlds, the prospect of an unbreakable interplanetary internet, or the chance to finally test the foundations of physics itself? Share your thoughts in the comments, and if you want to continue exploring the frontiers of science and technology with us, subscribe to join the journey.